Hi there. So in this series of lectures, we'll look at time in distributed systems. Time is a very important and challenging concept, and we have to either solve it as an issue or get around it in some way. So here's an example of why time is an important issue and why you need synchronization. Suppose you want to catch a bus at 6:05 p.m., but your watch is off by 15 minutes. If your watch is 15 minutes late, essentially you're going to miss the bus because you'll arrive 15 minutes late at the bus stop. If your watch is 15 minutes early, then you'll end up waiting quite a long time, 15 minutes extra, while you might have been doing something else that was more useful. So because your clock is not synchronized, because your watch is not synchronized, either you have a violation of correctness when you miss the bus, or a violation of fairness when you end up waiting too long for the bus. What about in the cloud? Why is synchronization needed in the cloud? So let's consider an example of a cloud airline reservation system. So this might be one of the online airline reservation sites that you go to book a flight. Survey receives a client request to purchase the last ticket on a flight, say ABC 123. It replies to the client and simultaneously timestamps the purchase with its clock as 9 hours, 15 minutes, and 32.45 seconds. It then logs it on disk. It replies OK to the client. Now, that was the very last C, so the flight is not now full. So A sends a message to server B saying the flight is full. B enters the information that this particular flight is full into its log along with its own local clock value, which happens to read 9 hours, 10 minutes, 10.11 seconds. Notice that this is different from server A's time because, after all, the two servers are not synchronized in terms of their clocks. Now, server C, a third server, comes along and queries A's and B's logs, and it finds that A has purchased a ticket on behalf of a client at 9:15, while the flight actually was full at 9:10. And this confuses C, and this may lead C to take actions that are in fact incorrect. For instance, C might assume that more seats have opened up on the flight, and that's not going to be good or correct for any of the passengers. So if A and B had been synchronized in their clocks, this issue would not have happened. If both the clocks had read exactly the same at any point of time, this issue would not have arisen. So why is synchronizing the clocks of different processes so challenging in internet-based systems like clouds? Well, each of the processes run on their own clocks. Typically, this is the system clock on the motherboard of the machine on which that particular processor is running, where this process is scheduled. But unlike the processors on a single machine which share the same system clock, in a distributed system, which is known as an asynchronous distributed system, which is an internet-based system, the different processes running on different machines don't necessarily share the same system clock. Essentially, all they share is a network through which they can send messages. Also, there are no bounds on how long messages take to get delayed, and there are no bounds on how long processes take to process individual instructions. This is what is known as the asynchronous distributed system model. This is unlike the synchronous distributed system model, which is true in multiprocessor or supercomputer or parallel systems where many processes share a single system clock. And this asynchrony makes it challenging to synchronize clocks because of the unpredictable message delays. And you'll see this quite soon as we go along. So some definitions before we proceed. An asynchronous distributed system consists of a number of processes. Processes is the plural of process, and each process is what you might normally imagine a process is. It consists of its own code, its own heap, its own program counter, its own stack, its registers, and so on and so forth. So all of these put together count as a process's state. Okay? This includes the value of its variables and everything else. Now, each process may change its state by taking actions. An action might be an instruction. It may increment a variable, and that changes that variable, so it also changes that process's state. Or it might send a message to someone else, to some other process, or it might receive a message from another process. These are the three kinds of actions or events that can happen in the system. An instruction, a message sent to another process, or a message being received from another process. Now, each process has a local clock, and events within a process can be assigned timestamps based on this local clock, because a local clock only increases linearly. It only moves forward. It never moves backwards, and it never gets stuck. Okay, so events within a given process at a given process can be ordered linearly. However, what we really want to do in a distributed system is order events across processes. We want to say that this event at process A and this other event at process B happened in this particular order, where maybe the first event at process A occurred before. So that's the challenge over here. So when you want to synchronize the clocks across different processes in a group, there are two terms that come into play. They are clock skew and clock drift. Clock skew is the relative difference in the clock values of two processes, while clock drift is a relative difference in their speeds, or their clock frequencies, or their clock rates. Think of this as two vehicles moving on the road. Clock skew is the distance between them at any point of time, and the distance may not be fixed. If the two vehicles are moving at the same speed, then the clock skew will stay the same as always. But if they're moving at different speeds, then the clock skew might change. Clock drift is the difference in the speeds of the two vehicles. Right? So a non-zero clock skew implies that clocks are not synchronized. So what we really want to do if we want to synchronize clocks is we want to get a non-zero clock skew. We want to get a zero clock skew. We want to have no difference between the clock values of the two processes. A non-zero clock drift, a difference in the speeds of the two process clocks, causes the two clocks to eventually drift, causes the clock skew to eventually increase. If the faster vehicle is ahead on the road, it will drift away and the clock skew is going to increase. If the faster vehicle is behind the slower vehicle, then it will catch up, and eventually then it will drift away well ahead in front, and the clock skew will eventually increase. So what we really want to do is we want to get the clock skew down to zero. How often do you want to synchronize the clocks of different processes? Well, this sort of depends on the maximum drift rate of the clock. The absolute maximum drift rate, or absolute MDR, is defined relative to the UTC time, which is the correct time at any point of time. The UTC time is maintained by correct atomic clocks at standards bodies. The MDR of a given process depends on the environment. Okay, so MDR is defined with respect to something, and when you say absolute MDR, it's defined with respect to the UTC. Now, the maximum drift rate between two clocks with similar MDR, with the same absolute MDR, is 2 times MDR. Why is this? Well, in the worst case, one of these clocks may be MDR ahead or faster than UTC. The other clock may be MDR slower than UTC, and so the relative difference between them is 2 times MDR. So given a maximum acceptable skew m between any pair of process clocks, clocks at two different processes, you need to synchronize the clocks once every m divided by 2 times MDR time units, okay, where MDR is your maximum drift rate that you know for the individual processes, and m is your maximum acceptable skew which the application can tolerate. Why is it m divided by 2 times MDR? This is the same reason as time equals distance divided by speed. Now, there are two terms that come into play when you want to synchronize process clocks. They are external and internal synchronization. In external synchronization, each process clock is synchronized with respect to an external time source, such as a UTC time source. So process I's clock may be at most d seconds in error compared to the external times clock. So Ci minus S, the absolute value of that, is always less than the bound d at all points of time. Okay, so examples of algorithms that try to achieve external synchronization are the Christian's algorithm and the NTP algorithm, which you will see later on in this lecture series. On the other hand, internal synchronization does not use an external source. Instead, the processes in the group themselves use each other's clocks to synchronize. And this means that if you want to bound inside the group, then you want to make sure that for any pair of processes I, j, the difference between their clocks, the clock skew between I and j, the absolute value of that is less than d. An example of an algorithm that achieves internal synchronization is the Berkeley algorithm. So the external and internal synchronization are related to each other. If you have external synchronization in a given group with a bound of d, this automatically implies internal synchronization with a bound of 2d. Why is this? Well, in the worst case, a process may be d ahead of the external source, and another process may be d behind the external source, so the difference between them in distance is 2 times d. But the other way around is not true. So if you have internal synchronization in a group, then this does not imply external synchronization with respect to any time source. In fact, the entire group may drift away as a whole from a given external source, and this is one of the disadvantages of using internal synchronization. So next, in the next lecture, we'll see some algorithms that are used and some techniques that are used in real systems for synchronizing clocks in cloud computing systems and in distributed systems.